In the late 1980s, inside a design bureau on the outskirts of Moscow, a small group of engineers was working on a problem that nobody had formally asked them to solve. The Soviet military already had attack helicopters. It had reconnaissance platforms. What it did not have, and what these engineers believed it desperately needed, was a single machine that could do both simultaneously, and do them well enough that it could coordinate an entire group of attack helicopters from the air, designating targets in real time, feeding fire control data to the strike aircraft orbiting behind it, and then delivering its own weapons against the most urgent threats while the strike package worked the rest of the target area. The concept was not complicated. The execution was. A helicopter capable of performing this role needed two things that existing Soviet rotorcraft did not combine effectively. It needed a sensor suite sophisticated enough to find, identify, and designate targets at ranges where the helicopter itself remained outside the threat envelope of most ground-based air defense. And it needed enough offensive capability that an adversary could not simply ignore it while concentrating fire on the more conventionally configured strike helicopters it was directing. A platform that could only observe was vulnerable the moment its escort departed. A platform that could observe and strike was a different tactical problem entirely, one that required the enemy to engage it directly rather than work around it. The design bureau working on this concept was the organization that had built its reputation on a configuration that most of the world's helicopter industry had largely abandoned: the coaxial rotor system, in which two sets of main rotor blades rotate in opposite directions on a shared shaft above the fuselage, eliminating the need for the tail rotor that conventional helicopter designs use to counteract the torque of a single main rotor. The engineers who worked there understood the coaxial system's advantages intimately and had spent decades refining it. They also understood its quirks, its sensitivities, and the specific engineering disciplines required to make it work reliably under combat conditions. Before we get into this story, if you find yourself genuinely surprised by what Russian engineers managed to build here, hit the like button and subscribe. This channel covers military hardware that the mainstream press rarely touches in depth, and there is a lot more coming. Drop a comment telling us which combat helicopter you think deserves its own story. Now, let's get into it. The foundation they were building on was an existing single-seat attack helicopter, a machine that had represented a significant departure from Soviet design tradition when it first flew, incorporating a level of agility and individual pilot authority that earlier Soviet attack helicopters had not prioritized. That aircraft had established the structural and aerodynamic baseline that the new two-seat variant would inherit. The engineering team's task was to adapt this baseline for a fundamentally different operational concept, transforming a single-seat strike platform into a two-seat reconnaissance and strike coordinator without sacrificing the performance characteristics that made the original aircraft tactically effective. The decision to seat the two crew members side by side, rather than in the tandem arrangement that most military attack helicopters worldwide used, was one of the first and most consequential choices the design team made. Tandem seating, one crew member directly behind the other, has aerodynamic advantages. The fuselage can be narrower, reducing drag and radar cross-section. The front seat crew member has unobstructed forward visibility. The rear seat crew member has a slightly elevated position that allows some forward visibility over the front occupant's head. The engineers chose side-by-side seating anyway, and the reasons illuminate the specific operational requirements they were trying to meet. In a reconnaissance and coordination role, the two crew members need to communicate constantly, rapidly, and with immediate shared reference to what each is seeing on their respective displays. In a tandem cockpit, communication between crew positions requires either an intercom system or raising one's voice over engine and rotor noise, adequate for procedural communication, less adequate for the rapid exchange of tactical information that real-time target coordination demands. Side-by-side seating allows the crew to see each other's displays directly, point at relevant information, and communicate with the immediacy of two people working at adjacent workstations. In the specific workflow of reconnaissance, target designation, and strike coordination, this mattered. The wider fuselage that side-by-side seating required was not without cost. The initial cockpit design that was presented to a military evaluation commission in 1994 was rejected specifically because the wider frontal profile increased the aircraft's radar cross-section to levels the commission found unacceptable. The recommendation was to redesign the canopy geometry to recover some of the radar signature advantage that the wider fuselage had cost. The engineers went back to the design, reworked the glazing angles and the forward fuselage geometry, and produced a configuration that satisfied the Commission's requirements at the cost of additional development time and expense. The timing of all this was important context. The Soviet Union had dissolved. The Russian defense industry was operating in economic conditions that would have been unimaginable to the engineers who had worked in the same buildings a decade earlier. Development programs that would previously have been funded on the basis of military need alone now had to compete for budget allocations that were shrinking in real terms every year. The work continued, but it continued slowly, with interruptions, with compromises driven by resource availability rather than technical preference, and with an awareness among the people doing it that the program might not survive to production if it did not demonstrate convincing progress at each stage of evaluation. The aircraft's first flight came in 1997, more than a decade after the initial concept discussions had begun. The sensor suite installed on the prototype reflected both the ambition of the original requirement and the practical constraints of what was available and affordable in the Russian defense industrial environment of the late 1990s. An electro-optical targeting system occupied the nose turret, combining a daylight television channel, a thermal imaging channel, a laser rangefinder, and a laser spot tracker that allowed the aircraft to follow a target that had been designated by another platform or by ground forces. The thermal imaging component in the initial configuration incorporated a sensor from a French manufacturer, a detail that illustrated the degree to which Russian defense programs of the period were drawing on international industrial relationships that would have been politically impossible in the Soviet era. The nose-mounted radar system that later production aircraft would carry was not yet integrated. The development of the full sensor suite proceeded in parallel with the airframe development rather than sequentially, which created a situation where the aircraft that first flew was in some respects a different machine from the aircraft that would eventually enter service. This parallel development approach was driven by the same budget pressures that affected every other aspect of the program. It was faster and cheaper to develop sensors and airframe concurrently and integrate them later than to develop one fully before beginning the other. The coaxial rotor configuration that defined the aircraft's mechanical architecture carried specific operational advantages that the engineers had designed around from the beginning. The absence of a tail rotor meant that all of the engine power was available for lift and maneuver rather than split between the main rotor and the anti-torque system. In a conventional helicopter, somewhere between 10 and 15% of total engine power goes to driving the tail rotor, power that produces no lift and contributes nothing to forward flight performance, but that is mechanically necessary to prevent the fuselage from spinning in the opposite direction from the main rotor. A coaxial helicopter recovers that power entirely, which translates directly into either greater payload capacity at a given gross weight or better performance at a given payload. The practical manifestation of this advantage was an aircraft that could carry a meaningful weapons load while maintaining the kind of agility that combat operations required. The maneuver envelope was genuinely aerobatic by helicopter standards. The aircraft was capable of figures that most military rotorcraft could not safely attempt, and these were not merely demonstration maneuvers performed for airshow audiences. The ability to execute steep banking turns, nose-high and nose-low attitudes at combat speeds, and the circular orbiting maneuver that allowed the aircraft to maintain a weapon pointed at a ground target while the helicopter itself moved laterally, all of these had direct combat utility. They allowed the aircraft to change aspect angle rapidly, making fire control solutions for ground-based air defense more difficult. They allowed the crew to maintain a targeting solution on a moving ground target without exposing the aircraft's vulnerable underside to ground fire for longer than necessary. The orbiting maneuver, flying a circular path around a target while maintaining the weapon system's aim point on the target throughout the orbit, was of particular interest because it solved a specific problem in attack helicopter operations. A helicopter attacking a ground target on a linear approach is predictable. The target's defenders know the direction of attack and can concentrate their fire in that direction. A helicopter that circles the target at combat speed while engaging it presents a continuously changing aspect angle to the defenders and can engage from multiple directions in rapid succession without exposing itself to concentrated fire from any single direction. The maneuver required precise flight control and a sensor and weapon system capable of maintaining target tracking through the continuous attitude changes of the orbit, and the combination of the aircraft's agility and its electro-optical suite made both possible. The production decision came in 2008, more than 2 decades after the initial concept work had begun. The aircraft that entered service in 2011 was substantially more capable than the prototype that had first flown in 1997. The development years had been used to mature the sensor suite, refine the aerodynamics of the nose section that had caused the original commission rejection, and integrate the full defensive systems package that operational requirements demanded. The production contract covered a substantial number of aircraft, including a naval variant designed for shipboard operations, a configuration that placed additional demands on the already capable coaxial system, since ship deck operations in sea states that produce significant deck motion require a helicopter that can handle asymmetric and rapidly varying aerodynamic conditions. The naval variant's development required addressing problems that the land-based version did not face. A helicopter landing on a moving ship deck in rough weather needs a rotor system that can maintain controlled flight through turbulence and gusting winds that would challenge any conventional aircraft. The coaxial configuration's inherent roll stability, a consequence of having 2 counter-rotating rotor discs that naturally resist rolling moments, provided an advantage in this environment. But it did not eliminate the engineering work required to qualify the aircraft for shipboard operations, and to develop the deck handling systems that allowed it to be secured and operated from naval vessels. The aircraft that resulted from all of this development had several characteristics that distinguished it from other combat helicopters in operation anywhere in the world. The crew ejection system was the most frequently cited, a capability that most military helicopters do not incorporate because the mechanical complexity of ejecting crew members safely past rotating rotor blades has historically made it impractical. The solution developed for this aircraft used a system that jettisoned the rotor blades fractionally before the ejection seats fired, creating a brief window in which the ejection trajectory was clear of the rotor disc. The seats themselves were qualified to function across a wide range of altitudes and airspeeds, giving the crew a genuine survival option in scenarios where a conventional helicopter crew would have no options beyond attempting a controlled crash. The fact that both crew members could eject simultaneously and independently without requiring coordination between them was operationally significant. In a combat situation where the aircraft was severely damaged and the crew needed to abandon it immediately, requiring one crew member to wait for the other's ejection to complete before initiating their own, would have introduced a delay that the tactical situation might not allow. The system allowed either crew member to initiate ejection independently, with the other seat automatically following within a fraction of a second. The armament philosophy reflected the aircraft's dual role as both a strike platform and a targeting coordinator. The primary fixed weapon was a 30mm automatic cannon mounted in a conformal installation that provided both azimuth and elevation movement. The gun was not fixed rigidly to the airframe pointing directly forward, but could be slewed within a working envelope to engage targets that were not directly ahead of the aircraft. The ammunition capacity was sufficient for sustained engagements, and the gun could switch between different ammunition types depending on the target: armor-piercing rounds against protected vehicles, high-explosive rounds against personnel and light structures. The external weapons load was carried on 6 hardpoints, distributed across 2 stub wings extending from the fuselage sides. The total weapons capacity of approximately 2 metric tons could be configured in multiple ways depending on the mission requirement. Anti-tank guided missiles represented the primary precision strike capability, weapons that combined laser guidance with tandem warhead technology designed to defeat reactive armor systems that had been specifically developed to counter earlier generations of shaped-charge anti-tank munitions. The dual-charge warhead fired a small initiating charge that triggered the reactive armor's explosive panel, and then immediately followed with the main shaped charge that penetrated the armor behind the depleted reactive panel before it could reset. The maximum engagement range of the primary anti-tank missiles, around 8 kilometers, was significant because it placed the helicopter outside the effective range of most man-portable air defense systems, while still allowing accurate engagement of armored targets. This standoff capability was central to the aircraft's survival philosophy. Unlike close support aircraft that achieved effectiveness by operating at very short range from their targets, accepting the risk that this proximity entailed, the helicopter's concept of operations was based on engaging from distances where the threat environment was manageable, using sensors capable of target identification and weapons capable of precision engagement at those ranges. The radar system carried on production aircraft could track multiple airborne and ground targets simultaneously, providing the crew with a tactical picture that extended well beyond what the optical system could resolve. Ground targets at the range and signature level of a main battle tank could be detected at distances that allowed engagement planning before the target was close enough to engage the helicopter. Airborne targets, including both fixed-wing aircraft and other helicopters, could be detected at ranges that provided warning time for defensive maneuvering or for engagement with air-to-air capable weapons. The air-to-air weapons capability was not a primary design requirement, but it was not an afterthought either. A helicopter operating as a reconnaissance and targeting coordinator is a high-value target that enemy forces have strong incentives to engage. A helicopter that can engage enemy aircraft at short range, not to achieve air superiority, which is not a role any helicopter can credibly claim against modern fighter aircraft, but to force incoming threats to maneuver defensively rather than execute their attack profiles undisturbed, has a survival advantage over one that cannot. The heat-seeking missiles that the aircraft could carry for the air-to-air role were not intended to replace the defensive maneuver, the countermeasures dispensing systems, or the electronic warfare suite. They were intended to add one more layer to a defensive capability that already had several. The electronic warfare and self-protection suite represented a substantial fraction of the aircraft's total systems complexity. A warning system monitored the electromagnetic environment continuously, detecting radar emissions that indicated the aircraft was being tracked by a fire control system, laser emissions that indicated a weapons system was designating the aircraft as a target, and the launch signatures of incoming missiles. Each category of warning triggered different protective responses, some automated, some requiring crew action, and the system was designed to provide the crew with enough information and enough time to respond effectively rather than simply alerting them that something bad was happening. The expendable countermeasures, flares and chaff dispensed from multiple points on the airframe addressed threats that the electronic warfare system could not defeat through jamming or deception alone. An infrared-guided missile tracking the aircraft's engine exhaust signature needed to be given a more attractive target. a burning flare, producing a thermal signature more intense than the engine exhaust, positioned between the missile and the aircraft to draw the seeker away. A radar-guided missile tracking the aircraft's radar cross-section needed to be confused by a cloud of reflective material that created multiple apparent targets, making the true aircraft position ambiguous. The specific flare and chaff formulations, the dispensing sequences that optimize their effectiveness against different threat types, and the timing logic that governed when automatic dispensing was triggered, all of this represented operational knowledge accumulated from decades of combat helicopter experience across multiple conflicts. The exhaust suppression system that reduced the aircraft's thermal signature before any defensive countermeasures were needed was perhaps less dramatic, but operationally important. A helicopter that radiates a strong, clean infrared signature is easier to detect and to track than one whose engine exhaust is mixed with ambient air before it can form a concentrated thermal plume. The mixing devices fitted to the exhaust ducts reduce the infrared contrast between the aircraft and its background, requiring an infrared seeker to work harder to maintain track, and in some engagement geometries, making initial acquisition more difficult for a searching missile seeker. The development of the modernized production variant represented an acknowledgement that the original production configuration, capable as it was, had been shaped by the technology available and the resources accessible during the difficult years of its development. The modernized version incorporated improvements that had become possible as Russian defense electronics technology advanced, and as the operational experience accumulated from fielding the original variant revealed specific areas where additional capability would have tactical value. The enhanced sensor suite in the modernized variant provided greater detection and recognition ranges, the ability to identify a target's type and threat level at distances where the original system could only detect that something was present. This distinction matters operationally, because a crew that knows it is looking at a main battle tank, rather than an armored personnel carrier, can select the appropriate weapon and set the appropriate engagement parameters before it is close to engagement range, saving time and reducing exposure. A crew that can only confirm target identity at shorter range must either engage earlier, with less certainty, or close the range before engaging, accepting greater risk from ground-based defenses. The networking capability that connected the modernized aircraft to other elements of a combined arms force, other helicopters, ground control elements, and unmanned systems operating in the same battle space, addressed a limitation that had always existed in the original concept. A helicopter that could see targets and designate them for engagement by other platforms was valuable. A helicopter that was integrated into a digital data network, sharing its sensor picture with every other node on the network and receiving their sensor pictures in return, was categorically more valuable. It was not just a sensor and a weapon. It was a node in a collective intelligence system that was smarter than any of its individual components. The coaxial rotor configuration that had defined the aircraft's character from the beginning carried a known limitation that the development team had worked around rather than solved. At specific combinations of rotor speed, aircraft weight, and altitude, the counter-rotating rotor discs could develop resonant oscillation, a vibration phenomenon where the mechanical excitation frequency approached the natural frequency of the rotor system, causing oscillations to amplify rather than dampen. The amplitude of these oscillations was measurable in centimeters under the worst conditions, which was large enough to affect the performance of sensitive avionics, reduce the service life of precision-guided weapons mounted on the external hardpoints, and, in extreme cases, create structural fatigue issues in components designed for much smaller vibration amplitudes. The phenomenon was not unique to this aircraft. Resonance problems are a well-understood class of mechanical engineering challenge, and every rotating machinery system must be designed to avoid operating at or near its resonant frequencies. But the coaxial system's particular dynamics created resonance conditions that were somewhat harder to predict and harder to avoid than those of a conventional single-rotor helicopter, and the operational restrictions required to keep the aircraft away from the resonance-prone flight envelope represented a genuine operational constraint. Whether the subsequent modernization addressed this issue comprehensively, or whether it remained as a background limitation on the aircraft's operational flexibility, was not publicly confirmed. The price of the aircraft, estimated in the range of $15 to $16 million per unit, placed it in the category of equipment whose loss is operationally significant rather than merely inconvenient. At this price point, the calculus of risk management changes. An aircraft worth this much cannot be used in the way that expendable assets are used. It cannot be sent into threat environments where loss is likely without a compelling operational justification. The sophisticated self-protection suite, the standoff weapons, the doctrine of engaging from ranges where the threat environment is manageable, all of these were partly a response to the aircraft's value, the recognition that preserving this machine was itself an operational requirement. This is the fundamental tension that every sophisticated combat helicopter design must navigate. The characteristics that make the aircraft effective, sensors that see further, weapons that reach further, electronics that process faster, also make it expensive. The expense creates a pressure to preserve it that can, if it becomes dominant, undermine the operational utility that the expense was incurred to provide. An aircraft that its operators are afraid to risk is an aircraft whose capability exists only on paper. The helicopter that began as a concept for coordinating other aircraft strikes had become, through 2 decades of development and operational refinement, a system capable of independent reconnaissance, targeting coordination, and direct strike engagement. A machine whose operational flexibility reflected the specific conditions of its development as much as the original design intent. The engineers who had started work in the late Soviet period continued through the resource-constrained 1990s and delivered a production aircraft in the early 2000s had built something that no other country had combined in exactly this configuration. Whether that configuration represents the optimal solution to the problem it was designed to address is a question that operational experience continues to answer. The coaxial system's advantages in power efficiency and roll stability come with the vibration sensitivity that the design team worked around rather than eliminated. The side-by-side cockpit that enhances crew coordination comes with the radar signature penalty that required the nose geometry redesign. The standoff engagement doctrine that preserves the aircraft comes with the limitations inherent in engaging at maximum weapon range rather than at close quarters. Every design is a set of choices, and every choice involves accepting some limitations in exchange for gaining some advantages. The question is whether the choices made serve the mission that the aircraft was built for. In the specific role of reconnaissance, coordination, and precision strike, operating at standoff range, integrating with ground and air elements of a combined arms force, engaging high-value targets with precision weapons while remaining outside the most dangerous portions of the threat envelope, the choices reflected in this aircraft's design serve its mission in ways that its operators have found genuinely valuable. That is the story of a helicopter that took the better part of 2 decades to reach production, that was shaped at every stage by constraints its designers had not chosen, and that emerged from those constraints as something that its original concept had described, but that no previous aircraft had actually embodied. The Alligator, as it came to be known from the moment it was painted black and given its name, was the product of engineers who kept working on a problem through years when the institutional support for doing so was uncertain, because they believed the problem was worth solving and that their solution was the right one. On the evidence of what they built, they were not wrong.